Hey everybody, so thanks for coming. We appreciate you coming, and we hope that you find this our talk useful, helpful, to give you kind of perspective on the kinds of things you'll learn in your coursework throughout the undergrad, and for more advanced, higher level students like seniors, maybe give you more information on stuff that you're learning in the higher level efforts. So this is our first workshop, technical workshop on demystifying hardware. So a series of workshops aimed towards demystifying hardware and developing with them and working with them in general. And this first talk is just a brief, or just like a broad introduction to computer hardware as a whole. And so I am the president of IEEE-CS. Brooks and Mateus is the secretary. And both of us are graduate students. I'm a PhD candidate, and he is a MS student right now. So we've been working in this space for quite some time, and we have pretty good knowledge in this area that we hope to share with you guys. And not only are we grads, but we also did our undergrad here at USF in computer engineering. So we are familiar with all of the undergraduate coursework and all the material that you learn throughout it. So, yeah. I kind of briefly went over this, but yeah, our goals for this for these series are to, one, teach new students, freshmen, sophomore, about computer hardware, computer engineering, clarify common misconceptions about computer hardware, and provide practical projects on computer hardware designs like FPGA using Verilog and VHDL coding, and logic design in future workshops where we work on more in-depth and narrow-focused workshops. And we're here to answer any questions that you might have about computer hardware, about anything in your coursework that you're taking right now.
Or you're planning to work
in
the future.
Yeah, and stuff you're planning on working on in the future. So we're hoping to really be a resource for you as you go through your hardware, even software courses. And moreover, we want to create an open space for you to socialize and network, collaborate, share ideas, and with regards to computer hardware, computer engineering. Especially like if you're really passionate about what you do, we hope that this can help you find other people who are also passionate about similar things, and you guys can network, and you can meet people and make project group members out of it. It's a really good way to learn and navigate through the terror of the undergraduate program. So our agenda for today is as follows. First, we're going to give you an overview of what computers are, what computation is, computer hardware versus computer software, and why you might want to learn more about computer hardware in general. We'll give a brief hierarchy of generic computer components and peripherals, and then we'll go over analog and digital circuits and how that pertains to the different types of hardware devices that we'll talk about. We'll talk about the different types of hardware technologies, like those for software processing, more application-specific hardware, so hardware designed for one purpose, and reconfigurable hardware that can be redesigned for different purposes. Then we'll give an overview of memory and storage technologies and standards, and then briefly go over some future directions like neuromorphic computing and quantum computing, some stuff that's really exciting right now.
And just a quick reminder, this is going to be all surface level. We're not going to go too deep in the math. Yeah. We understand a lot of that here are freshman students, so it's to give you an introduction to everything. So let's start with the overview. So first of all, what is a computer? It's any device that you can think of that does computations. Any. Does no matter like basic computer, it can be anything that can does kind of computation. More often use electronics or mechanical, but in the past, it used to refer to people. Here's an example of in the past where if someone creates an algorithm give it to a team of really talented women. There used to be a lot of women, like multiple tests. You give it to them, and then we'll start doing all these computations, follow the algorithm. Now that we have actual physical devices, so we don't need this talented woman to do the stuff, they can just help us also in the actual programming of hardware side. Now that we have this idea of it can be any computation, then what is computations? It's basically numerical operations. Any mathematical calculations, any numeric operations that you can think of, is a computation. So if you think of any device that does numerical operation, it will be a computer. And there's two ways that we can implement these computations. It can be through hardware, directly into the circuit, or software, more into a digital program side. Now, what is computer hardware? Well, it's going to be the physical, concrete, actual component of the computer. So any system that requires to do all these functions. So if you think of any application, anything you want to do, it will be the actual physical components. It could be the monitor, the mouse, keyboard, processor, memory, any physical components of the actual computer or device that you're working with. Alternatively, you can have a software. So it will be the virtual, abstract interpretation of this computer system. So on the layer, you have the actual computer doing stuff, and you can interpret it differently by looking in a different realm, which we will call like the virtual realm. And you can create programs that the computer will interpret it for you, and you can visualize it in different ways. So you can see as a code, you can see different things on the screen, you can interpret as a button, even though there's no actual button in the screen. But it gives you that illusion, so it can make it more easier to interpret what's actually going on in the computer. The difference between hardware and software. Well, first of all, software is virtual. It's not a real part. It's actually all make-believe to fool you that what is actually going on, to make it more easier for you to understand, versus the actual physical part, the actual circuitry behind it will be the hardware side. Software often refers to instructions or set of code, while the hardware is the actual circuitry or the materials that you work with. Software is not really required for all computers because you don't need to have the actual virtual part. You can just go straight to the hardware, but all devices need the hardware, the actual physical component. You don't need to make a virtual side for the software. If the software is damaged, you can always just back it up with a copy. If you have a copy, you can just back it up. However, the software, you have to buy a new one or repair. So you have to, most likely because devices are so small, most likely it's better to buy a new one since or the physical components in circuitries. It's hard to repair something nanoscale. Both can be fixed on can normally be fixed easily. Features added to the software, you just write more code, while hardware is really hard to fix bugs, much more complicated. It's basically an actual, the actual circuitry itself. And then software, typically it goes in serial temporal. We're going to talk more about that. And then the hardware tends to be more parallel, although you can also do serial, but in general it's more, you can parallelize. Now, this need two words. What is the difference between serial and parallel computing? Here it is, an example. Let's say we want to compute this quadratic equation, and we're given x, a, b, c. So one way we can do is, on this left-hand side, is go do one computation at a time. So first of all, we're going to load x into a register. Let's call register R1. Then we grab the value and multiply with the a value. Then they do the next step, which is add b. Then they do the next step to multiply with the already loaded x value, and then we add c. It takes at least 5 clock cycles. Well, in parallel, maybe you can do 2 operations at the same time. So over here you have doing the x squared, while here you have a xp. So at the same time, then later on you will have here doing the a times x squared from the previous page, and then the c plus xp, and then you go in here and do combine everything together. You can see this will take much more less time, but it will require more space. Here you can reuse almost 0. You can reuse the same CPU and just run one after the other. Here will take space. That's where the name is coming from. Temporal takes time, spatial takes space. Any questions so far? No? Any question from teams? Okay. So what are about computer hardware? Well, if you're an end user, you want to better understand the limitation capability of a device. So you have to understand that, hey, you can do certain things in your computer, you cannot do certain things, and you don't want to accidentally break your devices. Even though everything you can work software level, but it can give you a better idea of what is going on if you ever want to fix or help use the actual device anytime. Or also you can customize build your computer. When you write programs, when you're a computer scientist, if you're a programmer, you have one alternative. You can write a bunch of very terrible code and just expect the computer optimize it. Or you can try to write better code for your particular computer so you can use less data, less memory, much more faster, much more efficient, because if you understand what's going on underneath the layer of the computer, you can write code for that computer. And also for working with embedded systems, if you want to build robots, you want to build your own systems like sensor security, temperature control, any machine that you want to create, most likely computers, the computation part will help you build this kind of system if you're interested in this side.
Okay, so to give an idea, a better idea of what the hierarchy of software versus hardware works, and like basically on the top we have user level programs. So like your web browser, your calculator, your programming IDE, those sorts of things. Your applications and programs subside on the very top level and are written in high-level programming languages like C++, Java, Python, C#, those kinds of things. And those different languages have, their own sets of rules and systems in place to, verify that you're coding correctly, obviously. But they additionally have what's called a compiler, which will compile the code that you write in the higher level language down to like assembly language and eventually machine language. But also between the hardware and the applications and programs or software, you have the operating system, which basically is it's basically written in assembly language or a higher level language, and it kind of mediates the interface between the two. So like allocating memory and a processing core for a certain application, making sure that a certain application doesn't get access for security reasons, those sorts of things.
And to point out that the operating system up here, even though it's up there and it says between the hardware, it actually can be written in machine learning. So in machine language itself or assembly language. So it's built in a higher level language and then goes down into lower level. Mm-hmm. So in reality, it will technically fit. Mostly takes all these layers, but it technically should be up here.
Mm-hmm. And so when you compile your source code, first it compiles down to an assembly language, and the assembly language might be like x86, if you're familiar with that, or MIPS. And basically it's just moving data around in registers and doing like step-by-step computations. And then that will get assembled by the assembler to output finally a machine language, which is actually just the raw binary that just runs through the hardware. And the way that it's structured, all the assembly language and then the machine language is structured based on what instruction set architecture the CPU uses. And so like x86 is an example, I think, considered a instruction set architecture. And so below that we have like the microarchitecture, which is even finer detail of how the control of the CPU and data path is controlled. And eventually we get even further down into digital logic design, where you're actually designing the gates and wires that implement certain logic functions. and you know, on like a very, very nanoscale level, where like, I mean, some of the more recent CPUs have billions of transistors in them, billions of gates. So it gets really, really small, and that's what VLSI, where VLSI comes in. It's a very large scale integrated circuit design, basically. And I already hinted at it, but yeah, transistors designed using CMOS process, which are little electrical switches that'll switch on or off and implement those logical functions. And then those are, you know, realized basically with the molecules and atoms of electricity, electrons, that sort of thing.
Yeah. So the actual material itself. Mm-hmm. So we're going to technically try to concentrate more on this yellow area and not too much. Probably more over here, since this takes a little, it's a bit harder to understand, to build transistor from scratch, but we're going to try to stay on this more software level.
Yeah, we'll get down into digital logic design
eventually.
So some of the common PC components, this is probably very straightforward or standard to you. The main board or motherboard is the central circuit board that has all of the bus connections in it to you know, control or to enable communication between different devices on the board, like the processor, the CPU, which is used to execute programs and run tasks. The memory or random access memory, which holds programs that are running at the current time. It's very high speed and volatile memory. Yeah, the interconnections or bus wires, which are those connections between the CPU, the RAM, the I/O components, and you know, common PC hardware components like in your desktop PC, like peripherals. You would have like a storage device, like a hard disk drive, solid state drive, to store everything in a non-volatile memory. So when you turn the power off, it still retains all of that information in the device. I mean, same thing with external storage. You know, a hard disk drive or SSD that exists outside of the computer. The standards or differences between those would just be like communication data standards like USB or SATA. Wireless networking adapters that support different Wi-Fi protocols, Bluetooth protocols, and obviously the video and graphics card, which will, you know, generate all the images for your screen and do all the heavy lifting for those computations.
Okay, so there's two types of circuitry that we want to highlight: is analog and digital. So give you just a very roughest idea. So if you're thinking about voltage, okay, since our circuitry deals with voltages, there's technically how we design it right now. If you think of voltage versus time, the analog circuit will tend to change over time. It doesn't have any specific value. It can vary. It can be more sinusoidal like this, or it can be more messy. It can have different values. Compared to digital, it will be more discrete. So if there's like low, high, or always low. And this we can interpret it as binary. If you can see how this is going to introduce more into our digital realm, is that it only has two values. And for simplicity, instead of thinking of 0 on high voltage or some value, let's just call it 0 and 1, or low and high. That's going to be much more simpler to interpret. This is really good for computations, storage manipulation, digital transmission, because it's just a 0 and a 1, so it's really easy to store two values rather than comparing multiple values. Analog is more useful for sensors, so if you want to sense temperature, sound, light, distance, humidity, all that tends to vary through time. Also signal amplification like speakers, and motors, if you want to manipulate motors. So it's more complex circuitry, while this doesn't tend to be that complex. It's just a bunch of transistors, buttons, switches. Analog uses more resistors, capacitive inductors, so it tends to give the variation through time. Analog is sensitive to noise, so if there's like, I did it purpose of this graph, you can see that there's edges. Those tiny edges could be significant to your device, while here there could be like edges in here, but we only care like, oh, it passes this line. So it's, you can see like even if there's an error, normally this error in significance is high. At least that's how I care. I don't care if it's like it's slightly off or not. It's high. Compared or low. It's just high or low. I don't care what's in between. I put down normally not sensitive because if this is too small, like this, you don't give enough time to wait. That could be significant. But if you give enough clock time, enough time to wait, it's not gonna be that important. Analog tends to be asynchronously, so doesn't need to wait for a clock. Normal, while digital tends to be computing the clock, so you can wait, and then you will measure the actual value once you like rise. Like you see, like rises the edge, and I put dots where we normally will measure the data. So we will measure the data here, 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 or maybe the people in Teams cannot see, but there's dots on the blue graph. And that represents the data that we are, at the time we're measuring the data. That way we don't care about the rise. If whatever's going on at the other edges, if it's messy, we don't care. We don't care at particular moments in time, often when it rises. I will use a clock for that. And then analog tends to be more for electrical engineer. Electrical engineer prefer to concentrate more on the analog side. They tend to hate the digital realm. But computer engineers is the other way around. We prefer more digital. It's easy for me to understand just high and low. Compared to analog, it tends to be more complex to interpret. But that's not limited there. We don't need to be like that. We can have a combination of both. We can combine both. So for example, analog and digital are convertible. You can have something more crazy instead of having just binary ones and zero. You can just have it, just break it down into different crazier graphs. So for example, you can interpret this crazier red analog signal to a much more simple signal in digital. This is much more complex to write, to computate. This is more advanced signal. We're not going to talk too much about this transformation between them. We're going to just trade with simple binary ones and zero. It's more interesting to interpret. But this could be your connection between an analog circuitry, like a microphone, to your binary digital circuitry, like your computer. So you can see the sound from your microphone can come in as an analog signal, can be converted to digital, which will represent a sequence of zeros and one in binary, and that will actually be stored in the computer. It's easier to store binary than an actual analog signal. So that's why we do the conversion between them. But that's an idea. You can convert in between. Sometimes an electrical engineer might work with digital, and computer engineer might work with analog in some cases. But we tried as much as possible to stay with digital. As a computer engineer, computer science is much more easy to understand. So for now, I'm going to mostly talk about digital. Analog, let's keep it for IEEE, the electrical engineering side. So if you're interested in that, you can talk with the electrical engineers. So type of hardware computing technology.
Okay, so there's a lot of different types of hardware processing, like chips, available for many different purposes. So for software processing, we usually want something that's more general purpose, that can run, supports different compilers for different programming languages. Basically, these are just hardware devices that are, can process and execute different programs. And examples of those are like CPUs, GPUs, and microcontrollers. And then we have more application-specific hardware, which is a hardware device that is fixed on one particular task. So the hardware device, if I design a chip that multiplies two numbers, it can't do division, it can't do addition, it can't do anything else. All it can do is multiply two numbers that I give it. So it's a very rigid type of hardware construct. An example is application-specific integrated circuit, so it's a very original name. And then kind of in between the software processing of general purpose and application-specific hardware, we have reconfigurable hardware devices that can be reconfigured to perform different tasks. So think like an ASIC, but instead we have FPGA, field programmable gate array. which can be programmed to be like an Ethernet controller. Tomorrow it can be programmed to control a bunch of robotics. There's not really any huge limitations to what you can do with it. So it's a really cool platform to work with.
I would prefer to use the word reconfigure, even though it's called programmable. But
yeah.
I use, because it's not you actually program like similar way to just send code software. You actually reconfigure the actual circuitry by you send it a code, but it's just actually reconfiguring the hardware itself.
Yeah.
It's much more simpler when you go into what is going on. It's not actually things moving around, but the idea is that you actually reconfigure the actual hardware.
Yeah. So for processing software, as I mentioned, basically we use CPU, GPUs, general purpose processing units, basically. CPUs have a lot of different features. The main ones that are worth mentioning are they have a memory for storing procedures in sequential order. They have like a fast internal memory, a cache memory. They also have like your RAM, random access memory, which is really, it needs to be as high speed as possible for fetching different instructions and different procedures, and especially when it's multitasking, like your processor is running a browser, running your Spotify, running Discord, all those different things. So, RAM speed really affects how well the CPU can perform. The CPU has an arithmetic logic unit, or an ALU, that can perform any mathematical expressions on data. So, addition, subtraction, multiplication, that sort of thing. And then they have a controller unit, or a method of controlling the communication with other system components. So the control unit will control what operands are given to the ALU to perform and what operation to perform. It can control what data is fetched from memory and what instruction is next and those sort of things. So these features of the CPU enable support for a wide range of applications, and they make it very general purpose. And nowadays, CPUs, we kind of refer to a CPU as a singular unit, but they actually have multiple processors or cores inside of them that have their own ALU and control unit and all of that, and that enables the more parallel and multiprocessing type of functionality. And so these can be found, in your computer. Obviously, you need a CPU to run your computer. And you could, an example of a small CPU would be in a Raspberry Pi unit. So, a GPU is somewhat general purpose, but as the name suggests, it's really good for graphics processing. The difference between it and a CPU is that it has much more processing cores, and they're much smaller than a CPU core. So. A CPU might have 4 cores, whereas the GPU might have 1,200 cores or something. And the cores in the GPU have capabilities to perform complex math operations, and that makes them very good for displaying graphics, because you have to calculate a pixel value, pixel intensity for, millions of pixels at a time, and this, it can be done all in parallel on the GPU all at once. And similarly, they're very good for accelerating machine learning tasks, and so that's why you see GPUs very commonly used for training neural networks and that sort of thing, because it involves a lot of mathematical computations that can be done in parallel. And something that might take training a neural network might take a day on a CPU, maybe for a small network. It might take a few minutes or a few seconds on the GPU. And an example here is shown of the GPU where it probably looks familiar to you, where it has a PCIe interface that will slide into the motherboard, and the GPU is the actual GPU chip with all the processing cores is in the middle, and it has embedded memory around the chip, and the whole circuit board enables the communication between its memory and GPU.
The way to distinguish between the graphic card and the GPU is the graphic card is the entire thing, the GPU is just the actual processing unit for the GPU. So if you normally up here you will never see it, but like you normally see up top, that's when is where you see the GPU. You see it in a huge fan because doing all that many computations.
Yeah,
really.
Yeah, not even just the computations, but the memory can get really hot too. Like in more like the RTX cards by NVIDIA, they have a GDDR6X RAM, and that stuff can get up in the hundreds of Celsius. And yeah, so that's why you know, the card might be huge, but like 90% of that card is a heatsink. So.
NFM.
Yeah, NFM. So microcontrollers are a little bit different from CPUs, but they're also pretty similar. It's basically a small computer that has its own memory for storing its program. So it has one program that it runs, and not like, you know, a CPU where you send different programs to it and it manages, like, you know, multitasking of different programs. A microcontroller is usually used for one purpose, and additionally it has other internal components that aren't available in a microprocessor and a CPU, like an analog digital converter, ADC, the more onboard RAM, and other communication units like UART and for Ethernet and stuff, and other programmable I/O ports. As you can see there, the microprocessor has like a ton of pins. That almost looks like, you know, a newer AMD processor, judging by how thin the pins look. And the microcontroller has like a lot less pins, a lot less functionality, and that makes it very well suited for embedded systems applications because they consume much less power than CPUs, and you know, if we're building an embedded system, the microcontroller allows us to basically program more high-level functionality into the system. So we have an example here from the engineering expo that we had a booth for, where Mateus here set up a little embedded system with a Arduino connected to a LCD screen, a number pad, and speakers and buttons. And basically, like, the microcontroller on the Arduino has his program that controls the interface between those different components. And finally, they're really good for embedded systems because they're really cheap to mass produce compared to CPUs. They're cheap to mass produce and cheap to obtain. Like an STM32 is a very commonly used microcontroller for embedded systems, and you can get those for like, don't quote me on this, but like $10, like $20. Like they're really cheap. And I mean, you know, people who are like companies who are building like an embedded systems project or design product, you know, they buy in mass quantities. So they're really cheap and efficient for embedded systems.
Yeah, the main cause of the major cause of difference is due to the memory. The memory processor will have a huge amount of memory, while this one will have much more less because we are talking about smaller systems.
Yeah, and it also has like the cache memory in your microprocessor that's like designed to be as fast as possible. It's really expensive. So the memory in the microcontroller is going to be much slower, and you know, not too slow obviously, but slower because it doesn't need to manage you know, multitasking between multiple different applications and you know, fetching instructions. It just has the one program that it fetches instructions from. So on to the next part, the more application-specific hardware for ASICs. As we said before, it's basically just a computer chip that's made for one single purpose. Instead of like, you know, a sequence of instructions that are ran to compute something, the circuit realizes the computation by the electrical components that it's comprised of. So because of that, they have drastically lower power consumptions than general purpose hardware for, you know, that particular application. So This is an example here, actually, of Mateus's final project from the CMOS class, where they designed a 16-bit multiplier where two 16-bit numbers are inputted, and then the computation is performed using an adder tree, and then outputted into a 32-bit number. So if you were to fabricate this and test it, and evaluate like how much power it consumes for multiplying numbers, and then do the same multiplications on your CPU, it would be drastically lower because there's no other additional circuitry doing anything else. When your CPU is computing A times B, it has all these other cores and all this other circuitry in it that's still has power running through it. So it has a lot of static power consumption. And however, ASICs are very difficult to design, very time consuming, and have a very high lead time. Just because of having to develop them. You specify what chip requirements you have, and you partition which parts of the chip are going to serve which purposes, and then you actually do the design in RTL, a hardware description language, or by physical layout. As you can see in here, there's this component zoomed in here is just a transistor level design of a inverter, so it'll invert one signal. So that whole process takes a long time, and then during that you have to synthesize it and implement it in hardware, and then perform simulations and verify that it works by inspecting waveforms and stuff. And then you place and route it onto the given technology, so like 22 nanometer, 18 nanometer, whatever CMOS process you're using, and then the final design is going to be described using a GDS2 file, is what it's called, and that is what you would actually send to Taiwanese semiconductor manufacturing company, TSMC, or another manufacturer that has a chip foundry. You would send that GDS2 to them, and then they come back and give you 10,000 of these or something. So, and that process can take a very long time, like 6 months to a year, longer depending on how complex the ASIC design is.
Just to give you an idea, basically I have to sketch every single rectangle here, and represents, and each rectangle represents different material, metals, semiconductors, and so on. And this, if you see one blue of this, is a transistor. This will be equivalent to a transistor, so you can see, it's so small. Even the square is not small enough. It's much more smaller than a square.
You're actually laying out the metals, the polysilicon, and the pins or pads that connect the different parts together. So it's very, very tedious, and in fact, a lot of researchers are working towards automating it with machine learning. So it's a pretty exciting area of research. So CPU versus ASIC. I already kind of said that lower power consumption for ASIC. CPU runs software code, and ASIC is just the hardware. CPU only performs serial operations, sequences of instructions, whereas ASIC is enables parallelism, so calculating intermediate results or results in parallel, and so much more efficient power performance and area. And CPU is obviously much easier to design and debug. You have your IDE, VS Code or something, and you step through your software code, and you can find memory leaks, segmentation faults, that sort of thing. The ASIC is much more difficult to design and debug. Like I said, you have to set your own test signals and run through the whole process that takes a while to simulate those test cases, and then inspect the waveforms of the outputs to verify that your result is correct. And you might think it's correct, but you need to check all possible edge cases, all just with designing software, testing for edge cases. And it can take a very long time with an ASIC. There might be one small edge case that you're leaving out, and ASICs get more like, something like a multiplier is a little bit easier to design and debug, but an ASIC that's designed to like process neural networks or something is much more of an undertaking.
Like if you remember the image before, that's just a multiplication. So if you have to do more complexity, you have to design so many stuff, and it's going to take a while. Alternatively, if you see the question mark, there's something in between that might help make things a little bit easier.
So yeah, reconfigurable hardware is kind of like the intermediary between CPU and ASIC, general purpose and application specific. So FPGAs are really exciting. They're basically these hardware chips that are, you can actually view them as general purpose, since they can be designed to do a wide range of applications. Basically, it's a generic chip that you can buy anywhere. They printed on a certain board designed by like Xilinx or Intel or those are the two big ones. I can't think of any others. Basically, you get this chip, and it doesn't do anything. It doesn't do anything out of the box, really. I mean, it might have like a test circuit on it or something, but really the user defines what the functionality is, and that's done using hardware description languages like Verilog or VHDL. So you will learn this kind of stuff in computer system design, FPGA design, and maybe senior project if you do something working with FPGAs. So the structure of an FPGA is shown here. Basically, it's an interconnected network of configurable logic blocks, the orange squares. Those logic blocks will implement your logical functions and that are described in the Verilog or VHDL, and the logic is implemented as lookup tables. So a lookup table here on the right has 4 inputs, A, B, C, D, and the flip-flop, which is controlled by the internal clock, will latch the results of the output of the lookup table on every clock cycle, and then that's produced on the output. And so basically, a lookup table is like a multiplexer. It's like if you have A and B, say 2 inputs, and you want to implement A or B, the lookup table has 4 bits of memory because there's 4 different possibilities of A and B, 0, 0, 0, 1, 1, 0, 1, 1. And the memory in the lookup table would be programmed with that certain function. So A or B is like 0, 1, 1, 1. And basically A and B are inputted into it, and the output of the lookup table is just going to be the output of the function, even though it's just, you can think of it as it's literally just grabbing it from this little memory cell, but it actually implements your logic functions. And nowadays FPGAs, I think Xilinx FPGAs support up to like 6 inputs, and then Intel FPGAs support up to like 7. So yeah, those are the logic blocks that implement the logic functions, and then also the interconnection resources or switching blocks control how the logic blocks are connected to each other. And like if you have one that's implementing a certain function, like maybe one's implementing an addition, one's implementing a multiplication, and then you send them to another logic block that performs like subtraction on the 2 or something. I mean, just using arithmetic because it's easy, but it can be much more complex operations. And finally, the I/O cells or I/O pins, which can be then mapped to the logic blocks that produce the final output for the design. And those I/O blocks can connect to, like when the FPGA is on a particular board, the board has bus wires and stuff that are connected to the different peripheral devices. So like a pin block like that has maybe like 10 wire pins that you can connect to it. You can connect those into the FPGA and then control those signals on the internally in the design.
And then one major difference that you want to look, even though that chip is like that chip is already made, so you just work with the chip. So what you do, the difference is you send a binary code to program what each orange block is gonna do, what how the wires in between is gonna get connected with switches, transistors, and then the pins, if they're gonna be inputs or outputs or both. Yeah. So all that is programmed. You, like everything that is already set up, you just send the binary code to switch on and off a bunch of switches.
The design flows.
But that's much more simple than actually doing the actual circuitry itself.
So the design flow of FPGAs is much more simple than for ASIC. So you can design your describe your design using Verilog VHDL and do what's called behavioral simulation. So behavioral simulation doesn't really like synthesize the logic or compile the logic in any way. It just basically looks at the code, and then you use a test bench to send certain inputs into your design, and then you observe the waveforms on the output. So it sounds kind of similar to the verification or the simulation verification process on ASIC, but it's much easier to do. Once you've verified that the behavior of your design is to spec, like what you want, then you start going through the hardware synthesis and implementation steps for actually implementing your design onto the hardware. So the first step of that is design synthesis, logic synthesis, which you can kind of think of as compilation. Basically, it'll go through the HDL code and figure out, okay, you need this many flip-flops, this many lookup tables, this is how they are connected, that sort of thing. And basically, like, reducing your logical structure down to the components that are available on the FPGA. So the logic blocks and the flip-flops and other things. So once that is done, you perform functional verification. So it's an additional layer of simulation that's done after logic synthesis. So sometimes when you perform synthesis, there are bugs that don't really come up in behavioral simulation. Like an example could be like a certain bus or signal is always set to 0 or always set to 1 or something, and so then a bunch of the logic in your design gets pruned and removed, and then like say you had a really complex CPU core or something that you're testing on the FPGA, you run synthesis and then it says, oh, we only needed 1 lookup table. Like, that's not right. I would expect like thousands or hundreds of lookup tables, and that's once you get through that step, you kind of have a good solid ground to work on about actually implementing it on the hardware. So the second stage is design implementation, where the design is basically like placed on the FPGA and routed on the FPGA. So placement, like, is designating which parts of the FPGA are getting which functions, which components from logic synthesis, and then routing for actually routing the logic blocks together and then routing them to the outputs. Then you perform a static timing analysis to basically make sure that, after it's been placed and routed, will it meet the timing requirements? So if I have a clock frequency of 100 megahertz, it could be that like the path, the most critical path, like the longest path in the design, doesn't meet that constraint. It can't be driven by that fast of a clock. So you have to reduce the clock speed, go through the whole process again. And you kind of do this until you find like what the highest frequency is that you can operate at. And the final step really is bit stream generation. So, not really machine code, even though it's a binary file, but basically the bit stream is what is sent to the FPGA and actually programs the functionality into it. And at that point, you upload that to the board. And then you do in-circuit verification. So if it's connected to a bunch of peripherals, verify that it's working correctly. You can also use integrated logic analyzers to view internal signals on the FPGA while it's running. And Yeah, so once you're done with that step, remove any logic analyzers because they take up resources, and then you're all set to go. So we actually had an example FPGA application at the expo as well. That's just my little Basis 3 board. It's like a $150 board. And we had basically all the switches connected to RG and red, green, and blue for VGA. And the FPGA would take those input signals and then specify, that's the value that's going to VGA, and then it would implement the VGA protocol, like going row by row on the screen and sending that signal to the screen, and doing it, so if it's 60, I think the monitor was at 60 hertz, so it would be going row by row and doing the entire screen 60 times every second.
I just want to point out that even though there's a lot of steps, all of this from basically about here to here there's a software that will do all the stuff for you.
Yeah.
You just send these answers. You just send this. So it's basically a Verilog or VHDL code that represents what is your circuitry. And then you send that, and hopefully works, everything the program is doing nicely. Sometimes there's bugs in your code, so it could break. But you end up getting, hopefully, your actual design that you send to the FPGA. Otherwise, you'll have to write the actual binary, so no.
Yeah. So CPU versus FPGA, basically, the CPU runs software code, and the FPGA just implements a hardware design, and we have enable parallelism, serial operations. It's much more efficient power area and speed. The frequencies are typically lower, like a lot lower, like your processor might be at like 3.5 gigahertz, the FPGA might be at 100 megahertz. So it's not really, the speed isn't really realized in the frequency, more so that everything is parallelized and pipelined to be implemented more efficiently. They can still be, they're less difficult than ASIC to design and debug, but more so than CPU. And kind of just rehashing some of the same information here, but this diagram kind of gives you an idea of, like, on this end we have ASICs and different types of ASICs, or like embedded FPGAs, all the way down to FPGAs. And basically, higher performance, higher volume production, low area power consumption, but high time to market, and FPGAs are better for flexibility, reusability, low time to market, because I can just grab one off the shelf, and the only lead time really is the time it takes for me to design the Verilog VHDL.
Now, quickly, there's different types of memory and storage technology. So before we talk about processing of calculations, now how we store that information. So there's different types. Why there are different types? Well, there's between two major trade-offs. Either you want really high-speed read and write, or you want to have really high capacity and cost. So if you want to cheap circuitry the way you can store more data. And then another thing is, if you wanted to be store information while on or off the device, those are one major trade-off. Two main categories I could point out, it will be registers. It's commonly used inside your CPU for storing, like, to do the in-between operations. So if they're really high speed, but only temporal, you only last for one clock cycle or something like that during the operation. It's just only between operations. Then there's RAM, which is random access memory. This is commonly used for your main memory, where you store your instructions or any program or data that you're being executed. So the CPU will collect the instructions and the data often from the main memory. It's also used for your cache and your main memory, as I pointed out here. It's volatile, except for registers, means that it needs power to keep the data. Once you turn off the computer, all of this is gonna be done, erased. So how we keep this from getting erased? Like, I don't want to lose all my programs. Then we have RAM. RAM tends to be non-volatile. That means that it does not need power to keep the data. So it will have where you have maybe the computer have 500 gigabytes or a terabyte or something like that. That's the major component. The problem with this is very, very slow. So that's why we also have this in between the RAM and the register to speed up. But while programs are not being run, it will be here. This will have a copy of everything you can run and the things that are not being used. That way you can speed up everything. Although it's called read-only memory, that means it can only read, it's only for reading. Some types of RAM are also erasable, but erase like chunks of blocks or the entire thing. So it's much more slower, much more complex to write and erase data from it. That's why they're very, very slow or impossible, depending on the document. So this is mostly used for reading. You collect the information from there, and then do your work on copy. So
for efficiency too, I just wanted to add, when you delete something on your drive, that's part of the reason why it's not actually deleted right away. It's not like actually, those contents in the drive aren't actually erased. They're just marked as like not needed. And so when you need to write something else to the disk, you write it, it will write to those portions of the disk.
I have a question.
Yes.
So you said that it's impossible to write, but this is something I've always wondered, but you just said that you write.
It depends on the kind. There are multiple kinds. So for example, you can have a ROM, or you can have electrical erasable ROM. So there are different type of ROM.
Yeah, read-only memory ROM is kind of a misnomer, or like, you know, kind of confusing, but yeah. Like, yeah, some ROMs can really only be like programmed once, and really those are kind of like the more earlier types of ROMs. Like EEPROM is, you know, electrically erasable, so you know, it's a little bit more involved to erase it. There's other ones where like you know, you would have to erase it by like using like a magnet or something.
Or UV light.
Yeah, UV light, and the method of programming them is like not as straightforward as just like, you know, like dragging and dropping to your hard drive. You know, it's like you have to like connect something to a particular port or ports and then send the data to it, and you know, it's something that's done typically like for an embedded system. It would be done like at the manufacturer. It's not something that like the user could do.
We have improved a lot on that side when we get like further into this side. So for example, you have your hard drive and state it technically wrong, but it's because they're very slow on writing. So it's so slow that we try to avoid writing to it as much as possible. But definitely it's a much better improvement than having impossible to really write. SSD will be the fastest so far that I think of.
Yeah. Yeah, some types of it, like NVMe and stuff like that. It's really fast. So yeah, don't think of ROM as like, it's not really, you know, all hard disk drives or SSDs are read only, but it's kind of like you said, a designation to, you know, things that write really slow or don't write at all. You know, don't have a write interface available to you.
Most likely, just think of it, we were lazy to give a new name for this.
Okay.
We just decided to keep us ROM.
Think of it ROM/storage.
And then just to give you a little more picture-wise idea, so inside the CPU, the registers, then you have here your main memory, which is your FRAM. It has the storage. It's still very slow, so a way to speed up is adding multiple levels of cache. That is every time much more faster than the other. So this is fast, and this is kind of slower. But as you go down, you're going to see the size of paper, so you can store more stuff in there. And as you get close to here, you will have much more smaller. That's why you cannot store that much data in here. And that's why you need bigger stuff to store the things that you're not running. But the things you're running, you want to have it up here. That way it's much more faster. And then you start swapping content in between. Not all computers have 3 levels of cache, so we'll have like just 1 level or 2. But as we go down, we can have more levels. This will become much more bigger, so it's kind of not ideal if it's for small devices. For bigger, complex devices, this will it may or may not speed up. That's a constraint that computer architecture is trying to look at. And then you can have your secondary storage that we talked so far, you run. This is the additional storage where you have all the things that are not being run, plus the things that are actually being run. So everything in there for here, here up the primary memories where you have the currently running stuff. And then you have additional secondary storage by connected to a cloud or web or distributed file systems. So all that can be done remotely. So you can add more storage as you go. And if you look at the graph, you're going to see as you go up, faster read, but it becomes much more expensive and less storage capacity. And it's also to be more expensive. That's why it's much more smaller. We don't use as many. And you can see it tend to be like bytes over kilobytes. But you go down, you get down to kilobytes, megabytes, gigabytes, terabytes, exabytes. So gigabyte, terabytes, if you start multiplying by thousands, more. Because it's basically remote, you can connect to multiple web servers as you need. But the opposite, if you go up, registers are really fast. It can write and read in 1 clock cycle of your computer. But if you go down, you have 10, 100, 1 million. Like from 1 to go from 1 million. So it's really huge difference just from going to the, and that's what we said. You can see the difference. This is still fast. The difference of speed between RAM and ROM. So ROM 1 million to compared to 100. That's why we normally still keep it the word ROM for read so slow.
You really see the difference when you're doing like a lot of accesses at a time, or sequentially. Like if you have to access like something like over and over in main memory, it's going to be a lot slower.
The CPU try to use as much as possible the upper levels as much as possible since they're faster, but that's why more frequently used of the computer, the CPU. If there's data being down here, it will be less frequent because it will get pushed up, and then you try to stay up here as much as possible.
The register size is determined by the architecture. So like if you have like a 32-bit CPU or a 64-bit CPU, 32-bit registers, 64-bit registers.
And then, and also there's name Bolat and Bolato. This will get all delivery rates once you turn on. This does not. So that's why we need an additional storage for that.
So we'll briefly go over some future directions. So I think I failed to mention or bring it up when I was talking about CPUs, but that design, that architecture of main memory, fetching instructions, and being controlled by the control unit, and then having an ALU for computing arithmetic, is referred to as the von Neumann architecture, and that's like the most commonly used architecture for doing computations in hardware, really, at least for like CPU and stuff. The only thing is that it has a very, very huge bottleneck between processing and memory. And this bottleneck is becoming more and more of a problem as Moore's law starts to break down, where we can't make the chips any smaller, we can't make the components any smaller and more efficient. And also because of certain applications like AI and machine learning that involve doing like billions of like matrix multiplications, like multiplying two numbers and whatnot. It involves fetching like data from memory over and over and over, so it becomes a huge bottleneck for that, and that's part of the reason why GPUs are used. But even even though GPUs are used, they're not very efficient, and so neuromorphic computing has been a recent area of research towards kind of solving those problems in the von Neumann architecture. Maybe not solving them, but providing an alternative. So the idea is basically to design a computer chip that mimics the behavior of the human brain. So instead of having a main memory and control unit and stuff, like in your brain, you don't really have that. You just have a bunch of neurons, interconnected network of neurons that fire from with different values and stuff. Don't quote me, I'm not a biology expert. But basically the idea on the hardware level is to use analog components to store and operate on data. if you look up neuromorphic computing, you might find other things like in-memory computing is another term where the memory is basically part of the compute layer. So we can do computation and store data in the same place. This is really good for like machine learning and AI because we reuse the data a lot, and so we don't really need to fetch it from memory over and over. And this is enabled through some analog components like memristors, it's like a combination memory resistor. Researchers have found that you can like multiply two values using memristors just by, like it realizes the multiplication just in the way that the electricity flows through them. So it's much more efficient than grabbing A from memory, grabbing B from memory, and multiplying them. So very, very high level overview, but basically, yeah, neuromorphic computing is trying to design new hardware processors like the human brain that are very well suited for accelerating training and testing of neural networks and AI applications.
Then alternatively, if you another research is trying to do is quantum computing. Maybe you heard about this, but this is an alternative that they're trying to do to create a new computer, different technology, different stuff compared to our current computing. We're using, remember I showed you the graph of using voltage to represent 0 and 1. Alternatively, they're trying to figure out if maybe instead of using voltage or we just 1 and 0 for digital, we use the quantum states of very small particles. So for example, one quantum state they can use is the electron spin. So if you're spinning north to south, so up spin, we would call it maybe a 1. And if you're the other way around, we could call that a 0. And this will significantly improve instead of using an entire piece of wire, we can use much more smaller scale particles to store data. So that could simplify a lot. So he's trying to use this, and with this, if you use actual particles and use the quantum state, it can bring additional properties such as superposition, interface, and entanglement, which is something that happens crazy physics, but I'll add a little bit more of flexibility to what we can do. And electron spin is not the only one. We can use atomic spin, polarized photon polarization. There's all these small particles has quantum states. We try to select which is. I just selected those few just to give you an idea. There's many complex. So what we can do, well, we can change from binary to complex math or vectors. Very simple binary to much more complex math. If changing to that side, that's why it's much more harder. This path. Expand the computer's operations, what kind of operations you can do. You can do the basic logic, but then other more. Different circuitry components, everything changes. Now we're talking about atoms instead of just like voltage and stuff. New ways of communication, that's entanglement. So I can have like I can be over here, send you one entangled particle, I have the other entangled particle. And then let's say you're in outer space really far away, and immediately I want to send you information, I can just do something to this one and immediately give you information on this one. So it's immediately. So it's really fast. Maybe a worst case scenario would be at the speed of light. That's how fast it can go. Instead of having slow communication and stuff. They could improve a lot on the speed on that. And then new ways of storing data is using superposition that sometimes you can store both 1 and 0 in the same location. So I'm going to touch that real quick. So for example, before we have just 1s and 0. Now quantum, so we'll call this a bit. So it can be either 1 or 0. That's it. A quantum bit can be both. Can be both 0 and 1 or somewhere in between. Like you can have different values, and perhaps this value over here can represent closer to a 0, but store some information about 1. So if later on you want to do something else with that, you can work and extract a superposition idea. So you can have more storage information between. So instead of having 1 bit, so for every 1 qubit, so quantum bit, you can replace equality 2 bits. You can only store 2 values. So now Or in other words, n qubits can replace 2 to the n bits. So we have an exponential improvement. So we can, so it's an exponential improvement on how much memory space you're going to use in your device. So for example, if you have 1 kilobyte of memory, you can reduce it just to 10 bytes. So a kilobyte will be 1024 bits. You can reduce it down to just 10 bits, or quantum bits. So it's much more smaller. Of course, that's 1 terabyte, so 1 kilobyte. So if you talk about terabytes, take the log of 2, and that's how much will be much more smaller. It's a very significant improvement in time and space. And maybe we can solve many NP problems, non-polynomial time. So they're the slowest components. These are exponential problems. But if we have exponential benefits, we can solve some exponential problems. And then this is how the normally write is going to be a vector, a matrix. So it could be 1 and 0 or 0 and 1, and they can represent different quantum values. You can see that math become more complex as you use actual complex numbers and vectors. So instead of just being 1 and 0, it's much more complex. The limitations, well, one major limitation is the quantum computer does not solve any, like it doesn't add more computational power. What this means is that if we have infinite amount of time, if a classical computer cannot solve it, then the quantum computer can also solve it with infinite amount of time. So the main thing that we're trying to add into quantum computing is speed and lower storage, so that we have improvement. We only do improvement on most of the speed and storage and all this stuff, not really solving new problems, solving problems that could be technically done by a quantum computer, but are really high speed. That's the main difference. So NP problems technically solved by classical computers if you have infinite amount of time. That transmission to quantum entanglement, as I said before, you can send the qubits to the other side, and then you can modify one of them and it will give information to the other side. But once you do that, they are not reusable. You cannot reuse it again. So you're wasting. So that's why it's non-renewable. So you have to like either bring it back to entanglement again, or you have to, or most of the cases you can. So it's very messy. So that's why it's non-renewable. Current quantum computers are too large and expensive for average consumers. So it's just we only have like 1 or 2 or a few of them. Like IBM, this is an example one. You can access to a web server if you want to play with them. It's still accessible, but virtually. It's still you're using your classic computer to work a quantum computer, because they're huge and very expensive. And then also they only do a few computations. It's right now it's so huge and so complex that it only does like 2 plus 2, 3 plus 2. Maybe 10 plus 10 will break it. It's very simplistic computation. So you go bigger and much more complex. It doesn't like it. It's still in the beginning stages. I think that's it. Just to give you an idea, in the future we're planning to have more topics. We already completed computer hardware. This on the bracket on the right side represents the equivalent courses at USF that will touch those topics on the left side. Not sure if make a course which is will touch the Raspberry Pi, but definitely the Arduino. And we are planning to have more topics hopefully in the future. And then this section, this workshop series, this area over here, the Verilog FPGA, will be a more hands-on practical side. So we're hopefully, after we do this small introduction, we can get more working with FPGAs, writing code, so you can have fun with actual real chips, what we can do with them. And then maybe in the future, we're gonna have something like similar to hackathon workshop with FPGAs, so more maybe a hackathon. Yeah. Any questions?
So for the quantum